In this particular video, we're going to look at and prove the following theorem about prime ideals. We're going to let P be a proper ideal of the ring R. Then P is a prime ideal if and only if the quotient ring R mod P is a domain. Now, before we can prove this particular theorem, we have to understand a little bit of the logic, and we also have to understand what prime ideal and domain means in the context of the theorem. So before we start in on the proof, I want to actually look at those kinds of issues. So the first thing that I want to notice is that we have a major hypothesis that P is a proper ideal inside R that's going to apply in both directions of the if and only if theorem. So I want to get that written down. We have this major hypothesis that applies to both directions of our if and only if statement. And the major hypothesis is P is a proper ideal of the ring R. And we get to assume this hypothesis in both directions of our if and only if proof. Now, the next thing that I want to do is I want to look at what does P as a prime ideal mean in the context of this particular theorem? Well, P is a prime ideal is going to mean the following. Since it's already a proper ideal, it's going to mean that if we have A times B belongs to P, then A has to belong to P, or B has to belong to P. And then the final thing that we need to look at and talk about is what does it mean for the quotient ring to be a domain? And so let's think about what that means. R mod P is a domain means that R mod P has no zero divisors. But since quotient rings are just a little bit tricky, I want to actually think about what no zero divisors mean. Well, no zero divisors mean that you can't multiply two non-zero elements together and get the zero. So we need to think about what is the zero element. The zero element in R mod P is 0 plus P. But because of coset equality, this can also be written as little p plus p for all little p inside the ideal P. And that's what the zero element is. No zero divisors inside our quotient ring means the following. If we have A plus P times B plus P is equal to the 0 inside of our quotient ring, and I need to make that just a little bit clearer, then A plus P has to be the 0 element inside our quotient ring, or B plus P has to be the 0 element inside our quotient ring. At this point, we're now ready to actually look at the proof of the first direction, the forward direction of our theorem. So the forward direction, first of all, I want to state it. The statement is, let's let P be a proper ideal of the ring R. If P is a prime ideal, then the quotient ring is a domain. And here's the beginning of our proof. We're going to let P be a prime ideal. And I want to remind myself that the goal is to show that R mod P is a domain. So we need to show that R mod P has no zero divisors. Well, how are we going to show that R mod P has no zero divisors? Well, we're going to do the following. We are going to let A plus P and B plus P be any two elements of the quotient ring R mod P. And we are going to assume that A plus P times B plus P is equal to the zero inside the quotient ring. Now, what I know, though, is I know how to do coset multiplication. So this particular equation inside R mod P is going to say that we know AB plus P has to be equal to the zero inside of R mod P. Now, what does this say? Well, that says that AB has to be inside P by coset equality. Two sets are equal when their difference belongs to the ideal, and AB minus 0 is just P. So what do I now know? Well, now the fact that P is a prime ideal kicks in. Since AB is in P and P is a prime ideal, that means we know either A is inside P or B is inside P. But what does that statement say? A is inside P says A plus P is equal to the zero ring inside P, or B is inside P says B plus P is equal to the zero ring, the zero inside the quotient ring. So B plus P is equal to 0 plus P. So what we have now done is we have shown that if this product is equal to the zero inside the quotient ring, either the first factor is equal to the zero or the second factor is equal to the zero. In other words, at this point we can say that the quotient ring has no zero divisors. And that's going to be enough to say that the quotient ring is a domain. And that ends the proof of the first direction of our theorem. So we're now ready to prove the backwards direction of our theorem. And the backwards direction states that if we have P, so we're going to let P be a proper ideal of R. And if R mod P is a domain, then P is a prime ideal of R. And our proof, of course, is going to start with the assumption that we're going to let R mod P be a domain. In other words, we're going to assume that R mod P has no zero divisors. And I don't want to lose sight of what my goal is. So I'm going to write my goal down. My goal is to show that P is a prime ideal. And because I've already assumed that P is a proper ideal, what I need to do is I need to show that if A times B belongs to the ideal P, then either A is inside P or B is inside P. And I'm going to kind of box that in because I'm going to not want to lose sight of it. So what I want to do is I want to use the hypothesis that we have no zero divisors inside the quotient ring to somehow establish this particular implication is true. So I'm going to actually start with this particular assumption. We're going to let A and B be any elements of R with the property that A times B belongs to P. Now, since A times B belongs to P, we know that AB plus P is equal to the zero element inside our quotient ring. And now what I want you to do is to look at this. That particular equation will imply, well, let's see, AB plus P is A plus P times B plus P. And I need to clean up that plus sign. Well, that's just equal to this coset. So that coset must be the zero element inside R mod P. But R mod P has no zero divisors. Remember that? That's our hypothesis up here. So this particular equation inside R mod P says either A plus P is equal to zero plus P, or B plus P is equal to 0 plus P. And I know this because R mod P has no zero divisors. But look at what we now have. A plus P equals 0R plus P is going to say that A is inside P. On the other hand, if B plus P is equal to 0 plus P, then we have B is equal to, rather, that B belongs to P. And both of these are because of coset equality. And those comments at the beginning of the video about when two cosets were equal and what the zero inside R mod P is. But what I really want to look at is what we have accomplished. We started off with the hypothesis that A times B was inside P. And we now have that A times B inside P does indeed imply A is in P or B is in P. In other words, we have shown our goal. So, what we can say is that we have shown that AB inside P will indeed imply that A is inside P or that B is inside P. And that completes the proof of our theorem.